Rust programming course for beginners. This comprehensive course will guide you step by step through the fundamentals of Rust, enabling you to build robust and efficient applications. From understanding basic syntax and data types, to exploring more advanced topics like lifetimes and closures, Arfan Zuby will provide clear explanations and hands-on exercises to ensure you grasp every concept effectively. Get ready to unlock the power of Rust and elevate your programming skills to new heights.
Hi, my name is Arfan and I will be your guide in this comprehensive Rust course for beginners. So if you're interested in learning Rust, then congratulations, you have found the right course. So I've designed this course to ensure that you will learn Rust the proper way, using slides and visuals to illustrate concepts and providing exercises we will solve together. This means you will have an appropriate mix of theory and practice that will help you step by step mastering this new awesome programming language. And I strongly advise you to code along because you will learn so much more when actively participating rather than just watching the video. So let's dive in. So what are the goals of this course? First and foremost, getting familiar with core concepts and syntax of the language. We will take a look at data types and data structures, as well as ownership and borrowing. We will see how data is allocated in memory and how we access the data. And we'll take a look at standard library, generics, traits, lifetimes, and much, much more. Basically everything you need to become a great Rust developer. So why would you want to learn Rust? Now there would be, I guess, 1,000 reasons, but I have here put together some of the main ones. Now Rust is a really fast language in terms of execution time. It provides a rich type system. It doesn't have a garbage collector, which is part of the reason why it's so fast. It provides useful compiler outputs, and you will see that in the exercises we are solving. It guarantees memory safety, and it's the most beloved programming language since 2016 according to Stack Overflow, meaning now 7 years in a row. And we are experiencing fast adoption in various branches. Now over here you can see a table which shows various programming languages and their score in terms of energy efficiency and execution time. And as you can see, Rust is one of the languages on the top of the list. Now over here are some resources that you can learn with. Now I guess the main resource would be the Rust programming language. Really fantastic book and I recommend you to read it. Then there is Rustlinks. These are small exercises, basically programs which you have to debug. Then there is Rust by example. So if your style is more focusing code and less on text, then this would be suitable for you. And there is a website called Rust by Practice, and that is what we will cover together. And if you want to go more advanced, there is a book called Rust Forestations, and it's also very much recommended to read that. So before we dive into the first topic, I want to show you the website of Rust by Practice. And you can access it by going to the URL practice.rs. And this is the website. And over here, as you can see, these are all the topics we will cover together. Right? Now, this will be the first one, variables. And as you can see over here, we have small exercises that we will solve together. Now, before we start, I want to show you something else. And of course, we will keep up with the tradition and write a Hello World program. So you can go to the rustlang.org website. This is the official website of the Rust Foundation. And you can click over here, Playground. And as you can see over here, you can write Rust code and then execute it. And it's really cool because you even have the Vim key bindings over here, and you can even choose themes like that. And let's write our first program. So every program in Rust starts in the main function. This is the starting point of execution of every Rust program. And we declare functions with the fn keyword. So to print out to standard output, we can use the print line macro. As you can see, we write println exclamation mark, and then we can provide here the string we want to output. Like that. And then you can hit run. And as you can see, we have executed our first program. So congratulations. I hope you coded along. And now we start with the actual course. So variables. Variables are assigned using the let keyword. So if you're coming from a JavaScript background, this might seem familiar. You can print to standard output by the print or println macros. So print and println are basically very much the same, but println adds a new line at the end of the output. And scope of a variable is defined by the block of code in which it is declared. Now a function is a named block of code that is reusable, and shadowing allows a variable to be redeclared in the same scope with the same name. So let's solve some exercises. Binding and mutability. A variable can be used only if it has been initialized. Fix the error below with least amount of modification to the code. So again, we are starting always in the main function. Now over here we have two variables. And again, we declare variables with the let keyword, then the name. And over here we have a type annotation. Now don't worry too much for now, we'll cover that in the next topic to come. But for now, think of i32 as an integer type, right? And then we have here the assert eq macro, which stands for assert equality. So this macro takes two arguments and just basically asserts that these two are equal. In case they are not equal, the program will panic, meaning immediate exiting and returning an error message. If they are in fact equal, then the program will just continue executing. So as you can see, we want here that x is equal to a value of 5. So we can initialize x over here with a value of 5, like that. And to run this program, you can either click here or you can press Ctrl Enter. And let's read that over here, uninitialized but used error. So when you use a variable, it has to be initialized with a value, which makes sense, right? You can't use something which isn't initialized yet. Now y over here is uninitialized but also unused. This will only output a warning. Now over here you can't see the warning actually, but if I take this code and put it over here, as you can see, it gives us a warning unused variable y. Okay, to fix that we can prepend it with an underscore. Like that. Alright. Use mute to mark a variable as mutable. So in Rust, a variable in its nature is immutable, and you have to explicitly state that you want a variable to be mutable. So fill the blanks in the code to make it compile. As you can see, we are here using a variable x. So we want over here to declare x and initialize it with a value of 1. Now over here we are mutating x, which means this variable x over here should be mutable. And we do that using the mute keyword, like that. Now, this over here is shorthand syntax for this. Alright, so we take the value of 1, we add 2 to it, and then we assign it back to x, meaning x will then hold 3, right? Now, just a quick note, I will always try to annotate the type in this course. Most of the time it's not necessary. So when you see me annotating types, it's actually not because this is necessary, but just because I want to make stuff as clear as possible. So in this case, this would hold an integer type. And again, we will cover that in the next topic. Let's see. As you can see, this is compiling. X is equal to 3. Scope. A scope is the range within the program for which the item is valid. Fix the error below with least amount of modification. So over here we are initializing the variable x with a value of 10, an integer type. All right. Now here we have another scope. We also can call it the inner scope, and this would be the outer scope, right? So in this scope over here, we are declaring another variable, y. Now we over here try to print out x and y, and we can do that by placing inside the println macro these placeholders over here, and then providing as additional arguments over here the variables we want to put the values inside here. So for example, if we provide x over here, then this will get replaced by 10 because x is holding a value of 10. And as you can see, in the outer scope we are doing exactly the same. Now this program won't compile. And the reason is because a variable is only valid inside the scope in which it was declared. So for example, the variable y is declared inside the scope, meaning the variable y is only valid until this point. Alright, that means we can't use y here. So what would be the solution? The solution would be very simple. We just initialize the variable y in the main scope, in the outer scope over here, meaning x and y, both of them are valid until this point over here, right? Because this over here is the main scope. Let's see. As you can see, this is compiling. Fix the error with the use of define x. Now we can have other functions besides main. So over here we have the function define x, and as you can see, we are initializing a variable x which holds a string. Now this would be the type annotation for a string, right? Don't worry too much about the annotations now, because we will cover that, but just to let you know. Now, the problem here is that in main, we are trying to access x. Now in this scope over here, there is no variable with the name of x, which means that this program won't compile, because the compiler will tell you, I can't find over here a variable with the name of x. So what we can do over here is actually taking this line and putting it inside the function over here. Because as you can see in this scope of the function, a variable x has been declared and initialized. But if I run this program now, nothing will happen. And that's because, as I've said, the starting point of every Rust program is in the main function. Now, when we run the code, nothing will get executed. And that's because we have to actually call this function for it to do something. So in this case, we can call a function like that, just providing the name of the function and these parentheses. And as you can see, the output will be hello world, right? Because over here we are providing x to the print line macro, and we are appending to it comma world, like that. Shadowing. You can declare a new variable with the same name as a previous variable. Here we can say the first one is shadowed by the second one. Only modify assert EQ to make println work, print 42 in terminal. As you can see over here, we are initializing the variable x, which holds an i32 type, an integer type. Now in this scope over here, we are initializing another variable with the same name, x. But over here, we are initializing it with a value of 12 instead of 5. And that means when we assert the value of x over here, it should actually be 12, right? Now, what would be the value of x in this outer scope? If you said 5, then you're right, because this variable over here has been declared in the main scope, in this scope over here. That means x is holding a value of 5. Now in this scope over here, x holds a value of 12. And these are basically two different worlds, right? So the variable x declared in the main scope doesn't actually care about the variable x declared in this scope over here. They are separate. Now over here we are shadowing x in the main scope, meaning we redeclare and reinitialize the variable x, again with an integer type. Now when we output x, it should actually print out 42. As you can see, this will be the output. Number 6, remove a line in the code to make it compile. Now over here we have a mutable variable x, which holds 1, an integer type. Then we are assigning 7 to x. Now x holds 7, right? Then we are shadowing and rebinding. So we are redeclaring x and reinitializing it. And we initialize it with a value of x, meaning with 7, right? And then over here we are mutating x, and that means we are here incrementing x by 3. Again, using this shorthand notation, which would equate to that. And this would actually fail. And I want you to look at it and think about it. What over here might cause an error? So over here, as you can see, we are redeclaring x. And over here we are mutating x. Now, as I've said, every variable in Rust is in its nature immutable, meaning if we redeclare x like that, x will be immutable. Even if it was mutable over here, when we shadow it, then it will be immutable again. So what we can do over here is just using the mute keyword again, so x stays mutable. Now, you might ask, okay, why even shadowing? We can just assign a new value to x. Why is this even a thing? And you can see that here very good. So y over here holds an integer type, right? An integer 4. Now, when shadowing, we can assign to the variable a value of another type. In this case, for example, a string, right? So y will then hold a string type. Right, let's run that. And as you can see, this compiles. Now this line over here is completely useless. I hope you noticed that, because we are taking x and assign it again to x, which basically is the exact same thing as we had over here. So completely useless. Of course, they are doing that to learn the concept, but in real life, you don't need this line. All right, you can just do it like that. And as you can see, this also compiles. Unused variables. Fix the warning below with only one solution, two distinct solutions. So as you can see, of course, we want 2 stars, so we will do with 2 solutions. Now the problem here is that this program won't actually output warnings, right? So I will again copy that and I will put it inside the Rust playground like that. So if we run this program now, as you can see, we get a warning, unused variable x. Now, I have showed you that before. The easiest method would be to prepend the variable name with an underscore. As you can see, we don't get the warning over here. The second way would be to do it like that. This is telling the compiler that it should allow unused variables. So if you run it again, as you can see, no warning. So we have solved that. Destructuring. We can use pattern with let to destructure a tuple to separate variables. Now tuples, we will cover that in a later topic, but for now just think of tuples as a data structure that can hold various values, even of different types. So fix the arrow below with least amount of modification. So as you can see over here, we have a tuple, right, holding 2 integers, 1 and 2. And this over here is called destructuring. So we are using the let keyword, and we use this syntax over here to destructure these values into variables x and y. So x will then hold a value of 1 and y will hold a value of 2. Now over here we are mutating x. Now again, this variable here would be immutable, because in Rust every variable in its nature is immutable, and we have to explicitly state that we want to have it mutable. So what we can do over here, like we did before, we use the mute keyword like that. And then this should actually compile. So x holds 1 here, and then we increment x by 2. So x should in the end hold 3 and y should stay the same as it was. And as you can see, this is compiling. Destructuring assignments, introduced in Rust 1.59. You can now use tuple, slice, and struct patterns as the left-hand side of an assignment. So this is very useful actually. So we can declare two variables at once. So here we declare x and y, and this would be the same like writing let x and let y, right? So you're writing one line of code instead of two lines here. Now again, we declare here the variables, and we can then destructure these data structures over here. So we have here a tuple, and we are destructuring it. And notice over here we don't need to use the let keyword again, because we have already declared these variables over here, right? So we assign 3 to x, and this value over here we don't care about, so we can use these double dots over here. Now this over here is an array, and again we will cover that, don't worry. And this array holds two values. Now we don't care about the first one, but we want to destructure the second one into a variable called y. Now fill the blank to make the code work. In this case we have here an array, right? Remember, assert eq takes two arguments, and both of them have to be the same, equate to the same output, right? So what would be the value of x? It would be 3, because we have destructured here 3 into the variable x, and the same goes for here. We have destructured 2 into a variable y, which means y will then hold 2. All right, and we are done with the first topic. Easy start, and see you next time. Now let's look at numbers in Rust, and we'll start with integer types. Now an integer is basically a whole number, meaning it doesn't have a fractional part. And integers can come in two different forms. They can either be signed or unsigned. Now a signed integer can represent both positive and negative numbers. And I remember that because signed might stand for the minus sign that could be prepended to it. And unsigned integers are always positive integers, meaning they don't have a minus sign, hence unsigned. Now integers can come in different lengths. So there can be 8-bit integers, 16-bit, 32, up until 128 bits. And each length over here has two distinct types, one for signed and one for unsigned. So for example, if we have a variable which holds an unsigned 8-bit integer, we would type annotate that with the type U8. Or for example, we have a signed 64-bit integer, we would annotate it as I64. Now the last element in the table over here is arg, and arg stands for architecture. Now that means that the size of these two types, isize and usize, are dependent on the computer's architecture. Now I guess most of you guys today run computers with 64-bit architecture, meaning isize and usize have a size of 64 bits or 8 bytes. Alright, now the default types in Rust are for integers I32 and for floats F64. So if we don't annotate anything, the compiler will infer it to these types. Now my head is in the way. Now to make sense of all of this, you will have to understand the binary number system. Now, if you're familiar with binary, just skip ahead because you don't learn anything new here. But I just want to ensure that we are all on the same page. So if we consider this decimal number over here, 42, and let's look at each distinct digit. So we would have 4 and we would have 2, right? Now 2 would be in the ones place and 4 would be in the tens place. And if we would have more digits here, here would be the hundreds place, thousands place, and so on. Now, as you can see, we are here using a base of 10. Why is that? Because in the decimal system, we have 10 distinct digits to represent numbers, right? 0 to 9. And as you can see, we are here doing an exponentiation with an exponent of 0, because this is actually a mathematical rule which states that anything with an exponent of 0 will always evaluate to 1. So it doesn't matter which base you use, if you have an exponent of 0, the result will always be 1, right? 10 to the power of 0 would be 1, 4 to the power of 0 would be 1, and so on. And over here we have 10 to the power of 1, which would be 10, right? And then what we do is just we are multiplying the digits of our number with these exponentiations, right? So we would, for example, here 4 times 10 to the power of 1 plus 2 times 10 to the power of 0. Now again, 10 to the power of 1 would be 10 and 10 to the power of 0 would be 1. And then we would multiply these numbers together and then add this and we would have 42, right? Something which is very natural to you and you don't even think about it, right? Because decimal numbers are everywhere. Now in computers, things actually look a little bit different. Let's, for example, again consider the decimal number 42. Now this would be the binary representation of this number, 00101010. And as you can see, we have here 8 digits. Now a digit is called bit, right? And a bit is the smallest possible unit of information a computer can hold. Okay, now we have 8 bits over here and 8 bits make up 1 byte. And we over here have actually the same logic as we did over here, but with a base of 2, because again we can only represent 2 digits in a computer, and that's because a transistor can only be in one of 2 states. Either it's conducting electric current or it's non-conducting, 0 or 1, right? So the logic stays the same. Here we have 2 to the power of 0, which would be 1 because of the rule we have talked about. 2 to the power of 1 would be 2. 2 to the power of 2 would be 4. 2 to the power of 3 would be 8, and so on. And as you notice, the number here doubles. 1, 2, 4, 8, 16, and so on. Now, this over here is actually the fascinating part about computers to me personally, because it's just crazy if you think that everything represented, this video over here, and graphical models and 3D games and everything is stored and represented with only 2 digits. Mind-blowing, right? So we actually here do the same thing. We are just multiplying the bits over here with the exponentiations. Now we won't consider the 0 bits because anything multiplied by 0 will always be 0, right? So we are just caring about the 1 bits over here. So we are multiplying 1 times 2 to the power of 1, which would be 2, right? Because 1 times 2 would be 2. Then 1 times 2 to the power of 3, which would equate to 8. And 1 times 2 to the power of 5, which would be 32, as you can see over here. And then we are basically just adding these numbers together and we have 42. And this is the way your computer stores all of your data. All right. Now you might ask, okay, how far can we go with this? What would be the largest possible number we can represent? And let's for that see the range of 8-bit integers. So the smallest possible unsigned 8-bit integer would be 0, right? I hope this makes sense, because if we have a 0 in every position over here, the result will just be 0, right? Now the largest possible unsigned 8-bit integer would be 255. And that's the case when every single position over here holds a 1, right? And again, we are then just multiplying the 1 by the exponentiations over here and add it together. And you might now think, okay, 255 isn't a lot. What if I want to represent bigger numbers? And there is a simple solution to that. We are just adding more bits over here, right? Because the more bits we have, the larger number we can represent. So let's see, for example, a 16-bit integer. Again, the smallest possible 16-bit integer unsigned would be 0. And this is if every position over here holds 0. Now the largest possible 16-bit integer unsigned would be 65,535. Okay? And again, this would just be if we had in every single position a 1, right? Again, just adding the results of the exponentiations over here all together, and we would have this result. Now, as you can see, the more bits we have, the more we can represent. Now, what about signed integers? Again, signed integers can represent negative numbers. So signed integers use a concept called 2's complement, where the processor will take a number over here, for example 42, and this would be the binary representation of this number. Then it will invert this binary number, meaning a 0 becomes a 1 and 1 becomes 0. Right? Just inverting. And then after inverting the number, we add one single bit. Okay? So we add 1 here. This would then equate to 0, and we have a carry of 1. And then we add here 1, and we would have 1, and the rest stays the same. Now this would then be the binary representation of minus 42 or negative 42. Now the most significant bit over here is actually the sign bit. If it is 0, then it means the number is positive. If it is 1, then the number is negative. All right? And that's why there are distinct types for signed and unsigned. And the ranges for signed and unsigned integers vary, right? And over here we have an illustration just to see the ranges. For example, for I8, a signed integer of 8 bits, the range would be from minus 128 to 127. So the smallest possible number we can represent with a signed 8-bit integer would be minus 128. And the largest one would be 127. And as you can see, again, the more bits we have, the larger and smaller the integer can go, right? And again, unsigned integers never go below 0. Right, then we have usize and isize. So these are, as I've said, architecture dependent. So on a 32-bit architecture computer, the size of these usize and isize type would be 32 bits. On a 64-bit architecture, it would be 64 bits. And this is also called pointer-sized integer type, because it matches the size of a word in a given platform. So what is a word? You have to understand that the processor does not read 1 byte at a time from memory, it reads 1 word at a time. So in a 32-bit processor, it can access 4 bytes or 32 bits at a time, and in a 64-bit processor, it can access 8 bytes or 64 bits at a time. Now, if we look at this very simplified representation of computer memory, where we have over here addresses and over here the data, and each location over here holds data of 1 byte. All right. Now, in a 32-bit architecture, the size of a word is 4 bytes, right? 32 bits, which means that the processor can access 4 bytes at a time. So the processor will read this section over here as 1 word, right? It's basically a unit of data. And what you have to take from this is this statement over here. Usize gives you the guarantee to be always big enough to hold any pointer or any offset in a data structure. So the usize type can hold memory addresses which can point to any location in computer memory. That's very important. So let's see, floating point. There are two types, F32, which is of size 32 bits, and F64, which is of type 64 bits. Now the representation of these floats are according to the IEEE 754 specification. So let's look at some exercises. Tips: if we don't explicitly assign a type to a variable, then the compiler will infer one for us. Now, remove something to make it work. As you can see over here, we have a variable x which holds an I32 integer, right? Now, over here we have a mutable variable y which holds an unsigned 32-bit integer, right? So over here we are trying to assign x to y. Now this would actually fail because we can't assign a variable of a type to a variable of another type. It's not possible. So what we can do over here to fix that is actually just omitting the type. And this will then implicitly hold an I32 type, right? Because this is the default integer type in Rust. Now over here we are initializing another variable z, and what would be the type of z? Right, it would be I32, right? Fill the blank. So over here, as you can see, we have a value 38 which is of type U8. So we can also annotate a type directly on a value, meaning this value over here, 38, is of type U8. Now the problem here is that the variable over here, v, expects a type of U16. So we can't initialize a variable which expects a certain type with another type. But what we can do over here is using the as keyword. which basically can convert an integer type to another integer type. So we can use here as and U16. This will then compile. Tips: if we don't explicitly assign a type to a variable, then the compiler will infer one for us. Now we know that already. Modify assert EQ to make it work. So over here we are initializing the variable x with a value of 5. What would be the type annotation? It would be i32, right? It's the default integer type in Rust. Now in this assert EQ macro, we have here a string u32. We don't worry yet about this method. I will explain that in a later episode. And on the other side of the assert EQ macro, we have a function call. So we call type of with an argument of x. Actually a reference to x, but again, don't worry, we'll cover that. So when we call this function over here, it basically just gives us back the name of the type. So if we pass x over here, we would get back i32, right? Because this variable over here holds a value of type i32. Now this would then actually fail, right? Because we want here that type of x returns u32. So what we can do is just changing this type annotation over here. All right. Fill the blanks to make it work. Now over here we have a data type, for example i8, and the constant max. Now max just returns the largest possible number that can be represented with the mentioned data type. So for example i8 max would be 127, right? This would be an signed 8-bit integer, and we have seen the ranges. Now the max for an unsigned 8-bit integer would be 255. All right. Fix errors and panics to make it work. Now over here we have a value 251, which is of type U8, and we add 8 to it. Now in this case, the compiler will infer the types. So this would be U8, and the variable itself will hold an U8. Now, can you spot the problem over here? The problem is we have seen that U8 can only represent up to 255, right? So over here we would have 259. So this is not possible. So what we can do over here is just changing that to the next bigger data type, for example U16. Now then we have here a data type i8, a signed 8-bit integer, and we call the checked add method. Now this is actually the same as doing it like that, but in a safer way, because we have to handle the error. And unwrap over here, we will cover that. So this is actually a little bit safer, but it still will panic, because again, i8 cannot represent 259. It would be an overflow. So again, we can over here just say we want an i16, because an i16 can without problems represent 259. So v1 will then hold u16 and v2 will hold i16. Again, I'm just doing this for clarity. You don't have to annotate the types. All right, modify assert to make it work. Now, as you can see over here, we have numbers in different representations, or basically in different number systems. So this is decimal, this is hexadecimal, this is octal, and this is binary. Okay. Now the decimal over here has an underscore, and this is just a delimiter. So this is just for readability. It doesn't affect the actual value. Now let me convert that over here. We would have 2024. This is already in decimal system. Then over here we would have 255. Then over here we would have 63. And then over here, I hope you remember, this would be 255. Now if we calculate these, as you can see, the result would be this value over here. Like that. And this basically proves that in Rust you can perform mathematical operations on different number systems, right? Now floating point, fill the blank to make it work. As you can see over here, we have a floating point value. So what would be the type? I will annotate it directly. So it would be F64. This is the default floating point type, right? Now over here we have an F32, and over here we have an F64, right? Like that. Again, type annotations are not necessary. Now if we pass X to the type of function over here, what would be the return value? It would be F64, right? Make it work in two distinct ways. So if we execute this program over here, as you can see, this would panic. Now the problem here is floating point precision. The result won't be exactly 0.3. It would be something like that maybe, right? Or something like that. I don't know exactly. But the floating point value is too precise because the default floating point type is F64. So this is really precise, and that's why you have these tiny fractions over here. Now we can solve this using an F32, which is less precise, right? Like that. And this succeeds. Now, two distinct ways. We can also use the as keyword. Like that. So let me first move my head over here again. So range, two goals. First, modify assert to make it work. Second, make print line output 97 to 122. Now over here, as you can see, we have a mutable variable sum. What would be the type annotation? It would be I32. Okay. Now over here we have a for loop, meaning we are iterating over some range, and then we are executing an instruction inside this code block over here multiple times. Basically the times we are iterating over this range over here. Now in each iteration the variable I will hold a different value, right? So in the first iteration it would be -3. In the second iteration it would be -2. In the third -1, and so on until we reach 1. Why 1? Because 2 over here is excluded. And that's always the case when using this syntax. The endpoint of the range is always excluded. So we are iterating from -3 to 1. Okay? Now, let's actually do these iterations manually. So we start with 0, right? Now in the first iteration, I would be -3. So 0 plus -3 will be -3, right? So sum will then hold -3. Now in the second iteration, I will be -2. So -3 plus -2 will be -5. Third iteration, -1. -5 plus -1 will be -6. Then in the next iteration, I will be 0, so it doesn't have any impact. And in the last iteration, I will be 1. So -6 plus 1 will be -5. So the value of sum after this for loop will be -5. Now over here we again have a for loop, and this time we are iterating over a range of characters, namely from A to Z. Now this time Z over here is included because we are using the equal sign over here, which means we want a range from A to Z where the endpoint Z is included. And C over here will then hold in each iteration a character. So in the first one it would be A, then it would be B, then C, and so on. And we just print out the characters. Let's see how that looks like. As you can see, just printing out each character from A to Z. Now we want to have an output of 97 to 122. So let's look at the ASCII table. As you can see, in memory, a character would be stored as a numerical value. Now, of course, in memory, everything is stored as binary numbers, but it would be stored as the binary representation of these decimal numbers right here. So we want to go from 97A to 122Z, right? So it's actually pretty simple. Instead of outputting the C as character, we want to output it as an U8, for example, right? And then, as you can see, we have the ASCII code for the characters from A to Z, lowercase. Right. Then over here, exercise 10, fill the blanks. So we are here importing from the standard library the ops module, range and range inclusive. Now we have seen the shorthand syntax, and this would actually be the more verbose way to write that, but I think no one actually does it this way. Over here we have a range which starts at 1 and ends at 5. Now again, 5 would be excluded, right? Like that. Now range inclusive means we range from 1 to 5, where 5 is included. And we would write that shorthand syntax like this. 1 to 5 and 5 is included. Right, let's see the last exercise in this topic, computations. Fill the blanks and fix the errors. So as you can see over here we have integer addition. So 1 plus 2 will be 3. And the compiler over here will infer these types. So because we have over here an U32, an unsigned 32-bit integer, it will infer these values over here to be of the same type. All right. Now over here, the same thing. We have 1 minus 2 would be minus 1. And the compiler infers these types. Then over here we have 1 minus 2, which is equal minus 1. The problem over here is that we are dealing with an unsigned 8-bit integer. Now remember, unsigned integers can never be negative. So what we can do to fix that is just converting it to an I8, a signed 8-bit integer. And signed integers can represent both positive and negative numbers. Now over here we would have 150. And if there are no type annotations here, the default integer type will be inferred, which will be I32. Now over here again we have the problem of floating point precision, so we can cast that to an F32. Like that. Over here we have the modulus operator, and the modulus operator basically gives back the remainder of a division. So if we divide 24 by 5, we would have a remainder of 4. Now, as you can see, here we have Boolean logic and bitwise operations, and I want to show you some slides so we get the concept. Let's start with Boolean logic. Boolean logic deals with values that are either true or false. And there are three basic operations: and, or, and not. And over here you can see the truth tables of these operations. So let's see the AND operator. Now the AND operator takes two inputs and produces one output. Now the only time it outputs true is when both of the inputs are true. Otherwise it will always return false. In an OR operation, if either one of the inputs is true or both of the inputs are true, then it will output true. If both of the inputs are false, then it will output false. And the NOT operator will just basically invert the Boolean value. So over here we have not false, and this would evaluate to true. And not true will evaluate to false. Now let's see bitwise operations. Bitwise operations are operations that manipulate individual bits that make up a binary number, treating each bit of a binary number as a separate unit and perform logical operations on them. So it's very important that you get that in bitwise operations we are treating each bit as a separate unit, and we are doing some manipulation on each individual bit and not the binary number as a whole. And we'll cover here AND, OR, XOR operations and bitwise shifting. Now there are a lot more, but I will just cover the ones in the exercise. Let's start with the AND operator, this ampersand symbol over here. AND returns 1 only when both of its inputs are 1. So similar to Boolean logic, as you can see, the AND operator takes two inputs and produces one output. Now, as you can see in the truth table, if both of the inputs are 1, then the output will be 1. In any other case, the output will be 0. Let's see the OR operator, this symbol over here. OR